Yes, so hello, my name is Stefan Neumann. I'm a corporate trainer and consultant with the CCJENSEN in Denmark in the headquarters. I've been with them 15 years. I'm a mechanical engineer back in 1996, and I've been with Alfa Laval. I've been with Grundfos, it's a Danish pump manufacturer, and and the last 7 years also working as a licensed partner with the Noria Corporation, you know, the American company, through a licensed partner company called Clean Oil Consult here in Denmark. These certifications here, ICML, I don't know if you know them, but there's a ICML Machinery Lubrication Technician and Machinery Lubrication Analyst, and I'm level 2 on both of them. Yes, so that was very briefly about me. Today we'll be discussing contamination, what they will do to machines and oil, and the difference between an inline and an offline filter type. So you could say depth media versus more thinner media, and why we have two types for that. There may be a potential or an optional a future webinar where we can talk about sampling and analysis best practice and which analysis will verify everything is okay, maybe some online monitoring and so on, and that we may offer as soon as possible. If you're interested in that, you could then contact your normal CCJENSEN contact. So to start with, I want to say that the lubrication oil is actually like the lifeblood of the machine. You know, it's like in engines, gearboxes, hydraulic system and so on. It's very, very important that you have good, clean oil in there. It's similar like your body is having good blood. If your blood having bacteria and illnesses in your blood, you will get ill. The same with the machines. So what we want to do is we want to keep it clean, but unfortunately during any operation the lubrication oil will be contaminated with particles, water, acidity and oxidation. It's part of the same thing. That will reduce the lifetime of the machine, the reliability will be harmed, and the efficiency as well. And the studies have shown that 80% of oil related breakdowns are actually due to contaminated oil. So there's a huge amount of money in actually cleaning the oil and keeping it cool, clean and dry, as Noria say. In CCJENSEN, we're working with a principle called offline filtration, or kidney loop also called, and there's a very good business case around that. So if you compare to the inline filter here, the inline filter in a gearbox is supplying oil directly to the gear mesh and to the bearings and so on. But this filter is living a very tough life because of starting and stopping of a pump and other shock waves and so on. While the offline filter is connected to the bottom, to the sump here, and draws oil out as a slow pace and continuously filtering 24 hours back to the gearbox, hydraulic system, turbine, or whatever we were working with. So the good business case is primarily because you can reduce the cost for filtration, mainly because the filters hold a lot more dirt, so the dirt hold capacity is very big, typically 2 to 4 kilograms per insert. That will be 4 to 8 pounds in US. And CCJENSEN was one of the first companies in the world to work with offline filtration. We'll get back to the difference between inline and offline here at the end of this, so in about 25-30 minutes. The other company I work with called Clean Oil Consult, you can see there's a web page here. We do training for Noria in Denmark, Norway and Sweden, primarily Denmark at the moment, but yeah, you're welcome to see the web page here. So the topics of today is why it's important to work with clean oil. What about particles? What do they do? Water, varnish, and when fuel or diesel comes into lube oil, that's engines. And we'll talk, like I say, inline versus offline filter, and then end with some Q&A session. If you have questions on the way, like I say, you're welcome to type it into the instant message field. You may know that a lot of machines already have an inline filter, the pressure filter built in, which is taking care of the particles primarily, but they're not designed to keep the oil clean and make it cleaner and cleaner. So very often the oil will actually be more and more contaminated over the period of time. Also, the inline filters do not remove water, varnish, and sludge, so could I say, you're only focusing on particles. If you have a very good quality and very fine inline filter, it could be very, very expensive to run. So if you have a turbine, for example, with a 3 or 5 micron inline pressure filter, they are typically very big and quite expensive. So you could do it different in a different way, and we'll go back to that. So combining more types of filters. And there is a direct correlation between the contamination of the oil and then the cost for running. So you'll be having more wear if your oil is contaminated. You'll have more downtime. You'll spend more money on oil and components. So the cost of ownership is increasing if the oil is dirty. So if you want to save money and have a lower total cost of ownership, you need to work with the oil. One way of doing that is using an offline filter. Now this is a CTC filter, but other offline filters are obviously available. So what they do is they draw the oil from the bottom of the tank, or the bottom of the sump you could say, and slowly push it through a depth meter filter and clean the oil. What happens is after some time, typically depending on how dirty the system is, between 5 and 10 times circulation, the oil will get very clean. Then the oil would start to pick up dirt and varnish and water that is hanging around in the oil system. So on plate heat exchangers, on other, the bottom and so on. So it may take 20 times, it may take, up several hundred times circulation before the oil and the system is actually clean. But if you do it the right way, you can actually keep the oil clean and make the components and oil last longer. So the three main contamination we'll look at is, the first we'll look at particles. The problem with particles is that you cannot see them, those that are harmful for the oil system. The diameter of a human hair is around 70 micron, and a micron is 1,000th of a millimeter, and a dust particle dancing in the window will be roughly 40 micron. This is very, very small, and in an oil, if you took oil out in your hand or you look at an oil sample, you will not be able to see 40 micron like you can in air. In an oil, you'll be able to see a particle of plus 100, 150 micron or bigger, but not smaller. The problem is the majority of the particles that are very harmful for your oil system are actually in the region of like 1 micron, so tobacco smoke, or 3 micron, like bactericidal. So very, very, very small particles are harming your machines. And unfortunately, there's a lot of these small particles. So if we look at the small particles, there are roughly 70% of them are below 5 microns. So really, really, really small particles, and the majority of them are that small. If you go to about 10 microns, you see about 10% are bigger. That means 90% of the particles found in an oil system will be smaller than 10 micron. And why is it so? Well, if you think about a bigger particles like a speck of dust, 40 micron, that comes into a gearbox, roller bearing or whatever, and it's being crushed, that particle will generate thousands of small micron of like 1, 5, 10 micron particles. So there will always be way more of the small one than the bigger one. And also the bigger particles are much easier to filter out with a standard inline filter. So you'll typically have a curve like that showing a lot of particles in the smaller sizes. So if you have a roller bearing or a journal bearing like shown here, and you have room for maybe 10 micron where the oil is pumped in, but there's only room for 1 or 5 micron in the load zone, then you'll have metal to metal contact, pulverization of the particles, and that will create something called micropitting. I'll show you some photos in a moment, but this is small cracks in the surface that is slowly getting bigger and bigger. And especially when we're talking gears and roller bearings like this, there's very, very high pressure in this load zone. There's actually so high pressure that it deforms. It's called elasto-hydrodynamic lubrication. So the bearing is actually elastic because of the so high pressure. It's more than 35,000 bar, which I believe is something like, what is that in PSI, 150,000 maybe, something like that. Very, very, very high pressure. So you're actually deforming the ball and the racetrack. So of course a sand particle is very easily being crushed, but sand is harder than steel, even hardened steel. So a dust in the air or sand will easily destroy my surface. And that will look like you see here. This is from a coal mill, so yes, it is a contaminated area, but you can see here these spalls or these cracks, and that's because the surface is failing. When we're looking for these particles, we often use something called particle counting, and this is we're counting particle according to the ISO standard, ISO 4406, or some are using NAS standard. The NAS standard was actually changed back in 2001, I think it was, to an AES, but yeah, it's still being used, especially in offshore and marine and so on. But here you see a couple of membranes, and the reason I like to show the membranes together with an ISO or NAS count is because everybody can see the black one here at the bottom. This is a dirty membrane. So if you ran oil through that and it looked like this, and here we zoom in on the membrane, it looks like, you know, the moon more or less. Yeah, there's a lot of dirt and the numbers are high. So a NAS 12 on ISO count 23. So compared to one with an ISO 1196 and a NAS 0, you can see there's a big difference on the membrane. Mostly people are not using membranes, but they're actually using a laser particle counter that is counting the, could you say, the shadow of the particles that are obstructing the light, and this will then give a number of particles. For example, using a table, this 4406 is a table here where we're using the particles and putting or converting into a class. Now this table here is for 100 milliliter of oil. Some of you may be using 1 milliliter of oil, so the numbers you see here will be, you know, 100 times smaller on some of the tables you see in the US. So in Europe we use 100 milliliter. So as an example here, if we count, this is a new oil from a drum, we count the particles, 450,000 particles big or equal to 4 micron, 120,000 big or equal to 6 micron, and 14,000 big or equal to 14 micron. Instead of saying all this, I can move the numbers into this table. So 450,000 is between 250,000 and 500,000. That gives me a class 19. 120,000 is between 64,000 and 130,000. That is a class 17. 14,000 is between 8,000 and 16,000. So that's a class 14. So instead of saying this, I can say ISO code 19/17/14. It means this, so max 500,000 particles in 100 milliliter of oil, and that will be my 4 microns and bigger. You can see it says big or equal to. So the 14 microns are included in the 4 micron. What this table doesn't tell you is how I actually got the numbers. So the 450,000 particles in the 100 mil. How did I get that? Did I get it with the laser particle counter, or did I get it with the pore blockage or flow decay method, or was I using a membrane like I showed you before? It doesn't tell me that. So you can only compare the numbers if you're using the same technology or the same method for counting. Otherwise, there may be a difference. So using different labs, you will see a difference in these ISO counts. So a class 19 in one lab could be a 20 in another lab, or an 18. And as you can see, every time you are increasing one number, you're actually doubling the particle. So yeah, up to double, but of course there's a difference here. Maybe only a few hundred or a few thousand, you can actually go to the next class. So I like to have, you know, both the numbers of particles and then the class. But cleaning an oil, for example, this oil here in 1917-14, cleaning that and get it to instead of 19, get to a class 16, you can see I reduce half, half, and half again. So 64,000 compared to 500,000. That's quite a fall. Yes. So, and why you want to clean the oil is because of this, for example. If you have an ISO class of like new unfiltered oil, like I showed you before, in 1917-14, that is similar to a NAS 8. This you can use for low loaded gears, low pressure hydraulic systems, and so on. But what you're doing if you're running this system for 150 liter an hour, a liter a minute pump, so the main pump, 20 hours a day, 200 days a year, this will circulate 36 kilos or something like 70 pounds of dirt per year over that main pump. That will of course wear the pump. While if you had a 16, 14, 11 instead, or an S5, you would only be circulating 4 kilograms or 8 pounds. So 8 pounds versus 70 pounds, there's a big difference. So of course you'll be wearing out your pump. And the cleaner oil here, it says, is suitable for servo valves, high pressure hydraulic, common rail diesel, and so on. So the more of the dirty oil you circulate over the system, the more will wear. I've seen systems here in mining and cement, for example, where you're working with these ISO cars or NAS 11, and they get maybe 3 to 6 months life on a pump. So that is maximum maybe 4,000 hours. That is not good. I've also seen pumps working in clean oil that are 50 or 60,000 hours old and still functioning fine. So between 4,000 and 50,000, there's a big difference in how long you can have a pump lasting. This I collected from a lot of different supplier of systems here. So it's not all of them I agree fully with. For example, gear, here, the recommended for gears is an ISO code 181613. I would think that you need cleaner actually for gears, but yeah, that's what the OEM says, or the manufacturers. You can see here for engine lube oils, it says 1.5% weight, and that's because engine oil is typically very dark, so you cannot shoot a light through it and count the particles. Some labs are doing it, but they're diluting the oil maybe 1 to 100 or something, and then you're actually not looking at the particles in the lube oil, but rather in the solvent. So I would recommend to use weight percentage instead. But it's recommended if you want to extend the life that you run with an ISO code 161411 or better. So for all systems here, you can see hydraulics, gears, roller bearings, turbines, diesel, and so on. Engine could be difficult to run that clean, but most of the others is definitely possible. And why you want to do that? Yeah, now you can see this Noria table here. Each of the quadrants here are lighting up. That's because it depends on the machine type, how much you can extend the life. So this table here for where you have the gray area here, this is the current cleanliness of the oil, and you got your red area here with the expected cleanliness, so what you want to get to. And let's say that I have a system here, a hydraulic system, with an ISO code of 211916, and I clean it to a 161411. What will happen if it's a hydraulic? So I go from the 211916 here, sideways to come to the 161411, and this corner here where it says 4, that's my hydraulic and diesel engine. If it was a turbine, it would be 3 times longer life. It was roller bearings 2.5, and gearbox another 2 times. So between 2 and 4 times longer life of the components if I cleaned it from this ISO code to the other. Now it says, you will see here that some says 1.7, that's 70% extra and so on, but some are also saying above 10. Well, if you do it like in a lab and theoretical, of course you can do very good life extension, and of course that is possible, but in real life typically you do not see a machine that is running this dirty here. So a 24, 22, 19, that will be a crusher, for example, in a mine site that is with a dust seal and all seals are broken, then you cannot clean it to a 15, 13, 10. So yes, it's possible, but in real life it's actually not. In real life, A machine that is leaking so much dust in will never be so clean. It will maybe be clean at an 18, 16, 13, and then 6 times longer life. But it will, it will not be a hydraulic system, no gearbox. So that's one. So 2.5, 3 times. But 10 times you will probably not see in real life. However, it's a very good table to help you to justify cleaning the oil and get some much better life out of that. So we didn't like particles in oil because they destroyed our pumps, our valves, our everything. What about water? Yeah, water is also destroying my components because of different things. Well, water can do something called micropitting. That is, you see here a roller bearing. There's extremely high pressure in such a roller bearing, and the oil can actually solidify under this very high pressure, but water cannot. The water will collapse on itself, so implode, so not an explosion, but an implosion, and the water droplets will collapse on itself and create a very high intensity of energy pushing towards the surfaces and create a pit, so a small crack. And next time a ball is passing that crack, the high pressure oil will, be pressed into that oil crack and make the oil crack bigger and bigger, and suddenly you'll create a spall, a big area that will fall off the bearing. Cavitation can also happen. That's typically starting on the suction side of a pump. If you have water droplets in the oil, the water will turn into vapor or steam, and then when it gets into the pump, you'll get cavitation problems like you see in when you're having air and so on. This is just vapor, but it's the same problem. And the last word here, weird word, hydrogen embrittlement. What it means is that you're having hydrogen ions and hydrogen in the oil. Water consists of H2O. So when the hydrogen are migrating into the steel, it becomes brittle, like glass. And then you can, if you have a shock in a gear, for example, you can break a tooth because it's so brittle, and gear teeth need to be flexible or ductile, but they will not be if there's a lot of hydrogen in them. Water will cause these problems, but of course it will also cause corrosion. It will cause speeding up of degradation. We'll go back to what degradation or oxidation is, and varnish. It can deplete additives because a lot of the additives are actually can be washed out with oil because they are polar. ZDDP, for example, can be destroyed with water. You can create bacterial growth if you have enough of water there, and the micro pitting will look like this. So I'll show you a couple of photos here from Danish Wind Power Academy. Just take a sip of water. So this is from a wind turbine, but it could be any other gear where you have water coming in. So initially the first phase is these micro cracks, so micro pitting, and then hydrogen embrittlement, and these are bigger than fingernails, so big chunks of metal are jumping off. Here's again zooming in on a racetrack in a bearing. You can see the micro pitting or the micro crack. The other here is from Timken bearing. Now this is they're supplying a lot of bearings to water contaminated systems like in steel mills and paper mills. But you can get similar from FAC and FK and SKF and the other manufacturers. If you look at the life for the bearing here, so the L10 or the nominal life they look at, that is based on 100 parts per million of water in the oil, or 0.01%. So very little amount of oil. If you add 1,000 parts per million or 0.1%, you can see the curve goes quickly down. So about 1,000 parts per million, you have only 25% life of the bearing left. So you have just destroyed 75% of the life just by adding some water. And it's actually very little amount of water. You can calculate yourself what is 0.01% in an oil system with a few hundred gallons. It's a very little amount of water that is tolerated. And there's a lot of bearings out there that are running with way too much water in them. You may remember that we typically say oil and water don't mix, but a little bit of water can actually normally be mixed into oil. That is the dissolved state, so a few hundred parts per million can typically be mixed. So if I added some water to an oil that was running at the normal temperature, so maybe from 150 Fahrenheit or something like that, or maybe slightly colder, but in that region, 100 to 150, you can add some 100 parts per million to that oil. So that's like humidity in air. You will probably have something like 70% humidity in the room you're sitting, and you cannot see it. It's just dissolved in the air. Then if I add more water to the oil, I could create what is called an emulsion that will be similar to fog in the air. So there you can start to see the could I say, small globules of oil molecules that are actually creating like small bubbles in there, and that will be some types of oil. So engine oil will create a lot of these emulsified engine oil. You probably all know, as it looks like mayonnaise or something, caramel sauce. And if I add more water, then I'll have free water coming out. But that is not the same oil type. So turbine oil will typically go directly from the dissolved state to free water. It will not create any emulsions. And many gear oils and so on will not either. While if you have engine oil, it will not create free water unless you go to something like 30% water. Because of that, there's some international recognized water targets. So in hydraulic oil, you typically should aim at 200 ppm. For diesel or gas oil, 300 ppm. Gear oil around 500. These environmental acceptable lubricants based on esters, 1,000 or slightly less, and engine lube oil or glycols, 2,000. The glycols are very hygroscopic, so absorb humidity from the air, and they can take quite a lot of water before it actually starts to create emulsions or free water. The most important thing for all oil systems is that you will not have emulsions or free water, because that will create the problems we just discussed. Noria also made a table for water, similar to we had one for particles. So out here in the left side, the gray area, I have the current moisture level, and then it's slightly different made. So here I have the moisture level that I want to in the table, and then my life extension is in the red area here. And this is for bearings and gears and so on, where you have high pressure low zones. So if I took a system with 2,500 parts per million and clean it to about 150 ppm, you can see I'll go here, go sideways, now 156, very accurate in this table, and then gives me 5 times longer life. So that will be for a gear, for example. I could expect that. Now you could ask me, now if I clean both water and particle, will I then be adding 5 times longer life due to the water, and then 4 times longer life due to particles, for example? Well, in theory, yes, you can add them, but normally I would never do that. I would talk to you and say, what is your biggest issue? If you're talking as a steel mill, paper mill, or something where water is just flushing in, I would focus on the water, and then I would say, well, here you can get 5 times longer life if we would use the water level. Then the particles would just be an extra add-on that you will get some extra, but how much, will not look at that. If you had another application where you had a lot of dirt coming in, like a cement mill or a crusher or something else where there was a lot of dirt, I would focus on the particles and disregard the water, and then say, okay, you got 4 or 5 times longer life due to the particles. So that's typically how I would do it. Because when you look at adding them and you have 8, 9, 10 times longer life just by cleaning the oil, it gets a little too weird, a little too theoretically. So therefore I would normally pick one of them, and still the business case is fantastic. That's what I would normally recommend. So the last of the contamination here is aging of oil or degradation of oil. Now Oil is a natural product like milk, for example, and it can go off. You know, milk has a certain shelf life. So when milk goes off, it's typically due to temperature. The same with oil. The higher the temperature, the faster it degrades, or oxidizes, it's also called, because you need to have oxygen present. Otherwise, it's not oxidizing, or it's not degrading. Um, the more particles and the more water you have, the faster the oil will degrade. Primarily because my particles are actually creating wear, so you're getting hot spots in the load zone that are getting hot and destroying the oil, and also creating wear, more wear. So it's like a exponential growth of amount of particles. Also, my particles and water can actually deplete my additives. The zinc and phosphorus, for example, ZDDP here, and sulfur phosphorus, that's in gear oil, they will cling on to a particle and take a ride and go out to the bottom, for example. So, and these particles that are designed to cling on to a gear, they cannot see the difference between the steel in the gear and a steel particle that is floating in the oil. So they will take a ride on the particle or the water, and they will fall to the bottom. Well, you could then say, then some of the filters will take the additives. Yes, but if you don't have any filter, then you'll just destroy it even more. So the particles will take some of the additives. So you need to get the particles out as fast as possible. The more particles you have, the more the additives you will deplete. So when you're depleting your additives, you're getting a shorter oil life, and you need to change the oil. So you will create acidity, sludge, and varnish when the oil degrades. I'll just show you here. So when oil degrades, you'll have acidity, like milk. You know, you can smell milk that is off and it smells really bad. So the contamination will create something called sludge or resin, which is typically dissolving in warm oil. So if you have an oil of like 100 Fahrenheit, typically around that temperature, most of the varnish is actually not pleated out as varnish, but will be dissolved in the oil. When the temperature lowers, you'll create these varnish deposits, and most likely the viscosity will also increase. You see some photos. Now this is very, very hard, could you say, burned oil, so this is more like a thermal cracking and not typically how varnish is looking. I'll show you these instead. So this is how varnish looks in a hydraulic system. If you just pull the plug, so this is looking into the oil sump, and here they just pulled the plug, and you can see there's a lot of varnish and particles sticking here. Now this, if I don't remove that, my new oil will actually dissolve this back into solution, and then I'll be pumping it around in my system. If I have varnish on a hydraulic system, this is a steering machine on a ship, or if I have it here in a plate heat exchanger, I can of course create problems. So the most obvious reason for varnish consequences is when you're having fine valves that are sticking, or you lose control, so the valves cannot move. There's very little, tolerances in a valve. So between the plunger, moving plunger in the center of the valve, and the housing it says, so it's very easy to lose control over that valve. Also, if you have an inline filter, a very fine filter, you can restrict the flow because it's partially blocked with the varnish. This is also referred to as sandpaper surface. So this, if you see this, and that of course is a sticky layer with particles in, that's very abrasive. If you insulate a cooler like that, it will lose the efficiency, and you'll actually get hotter oil that can kill the oil quicker. And you can even bake it onto bearings, or so thrust bearings, for example, in the turbine, or you've also seen it maybe in an engine on the liner. You can bake it onto like a lacquer, and that can actually wear the engine quicker and start to use oil. So oil is with varnish is costing a lot of money. It means you lose availability and revenue, and you need to change your oil. So varnish is also quite costly for systems. So we have, now here's just a few photos of on a gearbox, on an engine, and a valve here. Now it's difficult to see, I know, but this is, there's more soot in this engine has been cleaned up. You can see it's yellow here. So you have a really bad combination of three things in most systems. So you have abrasive wear, so particles are destroying my surfaces. I have maybe some water that creates cavitation and pitting, and then I have water varnish issues. So these three things are big problems for most machines. There are some systems that also have issues with fuel. So that will be an engine, for example, where you're getting fuel into the engine oil. Now, fuel is a completely different chemical properties than oil, so it doesn't have the additives and so on. So you can create big problems and very fast degradation of the oil. Most problem is in regards to viscosity, because fuel, diesel for example, has much lower viscosity than engine lube oil. So you'll be decreasing the viscosity and create really bad, it's called adhesive wear in your bearings. If you're running the engine on heavy fuel, you'll see an increase in viscosity, which is also bad. Your flash point will also be harmed. Mostly oil will have a flash point about 240, 250 C. So what's that in Fahrenheit? For I think 400 or something like that. But it can get very, very low if you have too much ingression of fuel. In fact, so dangerously low that you can have a fire in the engine. And that's of course not good in the engine sump. So it could be from a leaking fuel pump, or a nozzle, or like you see here, cracked injector, or the needle valve you have in a common rail diesel engine can also be leaking fuel into the engine. Or like this one show a poor spray pattern where you're not atomizing the fuel, but more like sending a flow of fuel in the combustion chamber. Fuel will also have problems with your filter. You need to replace your filter. You can also have water in the fuel that will create microbes, or diesel pests it's called, and of course pitting and wear on your injectors and pumps. This is a diesel pest you have here. So this is the diesel feeding of the diesel pest feeding of the diesel, and then when the microbes die, they become like slimy stuff here in the bottom, and you don't want that in your engine or in your filters. You'll also have sandblasting of your fuel pumps and injectors and so on, the more dirt you have in the fuel, and ineffective combustions, and so you'll be using more fuel. So dirty fuel can easily cost a lot of money. Now, if you look at a vessel, or you look at a mine site or something where they're using a lot of engines or gensets, very quickly you can spend $100,000 on new injectors, new pumps, and so on yearly. I've seen some areas where they say the injector life would be normally 18 to 20,000 hours. But if they're having issues with dirty fuel, you're seeing 2,000 to 4,000 hours of injector life. So you are almost getting a tenth of the injector life compared to what it should be. So huge amount of money you can spend on that. Yes, so when you have dirty oil, it will exponentially create more and more wear in your system. And like I said in the start, studies have shown that the majority of breakdowns are actually due to contaminated oil. So some particles that are getting in will create more wear, more particles. So we need to get rid of this as soon as possible. So you can actually do that by thinking three types of filters. So you should stop the ingression of dirt and water. So you need to have some kind of air vent or breather system that makes sure the air that the system is breathing in is free from particles and water. Also, the system needs to be completely sealed. I mean, you don't have a manhole cover open, for example. So seals on your covers and good seals on the other open areas, so you don't get dirt in. You may think that most systems it's only hydraulic systems that are breathing, but actually most systems are breathing because of the temperature changes. So if a system is warm, the warm air takes more room, but when the air is getting cold and the oil is getting cold, it will actually take less room, and therefore it will suck in new amount of air. And if that air is dirty or wet, then you'll get the the dirt and water into your oil system. Then you also need to have an inline filter, a pressure filter here after the main pump. This is the last chance for the to stop the dirt getting into the system, and you can combine that with an offline filter that runs 24/7 from the most contaminated area here. I will just show it in a different way here. So if you look at the particles here and the percentage here, maybe you remember this curve here. So they have so if your inline filters is something like 6 to 30 micron, you're taking the bigger particles, but you're still leaving a lot of the small ones left. So your offline filter could be taking care of 3 micron or smaller, so you're taking much more of the whole curve here of particles. And your breather may be a desiccant breather if you're in a humid area. The one I've just shown here is with a bladder on the top. It's called a hybrid breather. So the bladder is contracting and expanding depending on the the normal breathing, and then a non-vital valve will open if there's a lot of breathing going on, and you'll suck through the filter and the desiccant here to take the water out. So typically your best combination for total protection and the cheapest way to clean an oil is actually to have a 10 or 12 micron breather, a 10 micron inline filter, and a 3 micron offline filter. Yes, so these system here, what is the difference between those two types of filters? So my inline pleated filter and my offline depth media. If we look at the inline filters first, they are typically a very thin sheets of pleated filter, pleated like you can see here, to get as big surface area as possible. Here the full flow is most important, and your low differential pressure. That calls for a thin media. If I had a very thick, very dense media in my full flow filter, that would mean I would maybe lose, many hundred psi or thousands of psi on the way. And of course I don't want that. My main pump should not be delivering an extra amount of psi just because the filter is taking some. So here the filter needs to have a low differential pressure over the filter as possible. And of course it needs to hold back as many particles in one pass, single pass as possible. So here your beta rating or your efficiency in one pass is of course important. But your depth media that you have in your offline or your kidney loop circle, there it's much more important that you have room for particles. So if you have higher differential pressure, it doesn't matter. You need a thick media that can take as much dirt as possible. So room for particle, also water and varnish if possible. So taking all your contamination out. Some filter types are even possible to take out acidity. Here in your pleated, your inline filter, you want the low differential pressure, and in your depth media, the kidney loop, it doesn't matter if the differential pressure is bigger because you have your own pump and you decide the flow rate. Why are people using cellulose? For example, CCJENSEN is using cellulose. Well, if you look at the surface area, so specific surface area for the cellulose type that CTC filters are made of, they have 120 square meters per gram. That is very difficult to understand. But if you compare it to glass fiber and synthetic polymers that are used in pleated inline filters, they have about 10 square meters per gram. This is crazy numbers. You could think that this is the best in the world, but it's actually not. If you look at activated carbon, there's about 300 square meters per gram, up to 1,000 square meters per gram. Even in your lungs, you have 70 square meters of specific area. And I look at myself, there's not 70 square meters on that. That's like 700 square feet in my lungs. But it's of course because you have all these small, hairs or whatever you want to call it in your lungs. And the same with the cellulose. There's these tiny hairs on each cellulose fiber. So there's a lot of specific area. So the whole fiber has the whole filter has a lot of cavities where the particles get trapped, and that is much larger than a glass fiber or melt blown pleated filter. And also because cellulose can absorb water and varnish, it adheres to the surface of the fibers and then absorbed into the fibers. So you get 3-in-1 and even 4-in-1 if you have acidity removal as well. If you just do a calculation, a CCC insert called the B2727 that weighs 3,600 grams, that is equal to 60 football fields of surface area. That is crazy. So if you think about it in layman terms, then you're taking oil and you're pouring out on the table in front of you. That will be your pleated inline filter. That will be your table. So if that would be a membrane or mesh, you want to pour the oil out on the table and let it seep through, and then that's how you clean it. If you're using a CCC filter, you're pouring the same amount of oil over a football field. And obviously you're getting much bigger area where the oil can seep through, and therefore you got room for much more dirt, much more water and varnish and particles and all that. That's why we're using cellulose. If you zoom in on the glass fiber versus cellulose fibers here, you can see this is glass fibers here, quite uniform in sizes here, and what obstruct the particles is obviously how the big the holes are here. If you zoom in on cellulose, CCC cellulose, you can see there's some big structural fibers here. They're about 20, little less than 20 micron. They are the ones that are, could you say, holding the fibers in place. And then there's a lot of tiny ones. These are called nanofibers. This is actually a patent or secret from CCJENSEN. So that helps you to do much finer filtration and to take as much varnish and particles and water out as possible. This is why you can do something like that. Here, a startup or hydraulic system here, you cannot see through the bottle, the tape on the wall. After 4.5 hours, you start to see it, and after 24 hours, you have removed the particles and the varnish from that. And that is only because you're using this depth meter that can take the varnish and the particles out. Yes, that was what I planned for my minutes, and yes, the time is definitely gone. So I'll be stopped.